So the rotor blades would be spinning so that this piece right here, since it's going down like this direction, this piece here is going to be coming out at you. This part right here is going to be going away from you on that end, and so the angular momentum would be upward, because once again we take our right hand, we wrap it so that our fingers on this side right here will go into the board. The ones over here, they come out of the board, and our thumb goes up. In the case of the picture that's on the bottom, where the helicopter is facing us, is in that case so at this point right here, it's coming towards us. So that would mean that on the from the helicopter perspective, on the right side from the helicopter's perspective would be coming towards us. The left side would be going away from us, and then the angular momentum would once again wrap our right hands. We see that's pointing up in that direction here. So okay, so this is our situation to start with here. That's the direction of the angular momentum. Now in this case it says the blades are going to increase their speed, and so if they speed up, they're going the same direction. That means that since our angular momentum is I omega, we have not changed anything about the moment of inertia of the blades. They weigh the same amount, their distribution in the same place here, but we have made omega go up. And so in that case is that since we're not changing I, we're making omega go up, is the angular momentum must go up of the blades. Now the problem is that the total angular momentum of the whole helicopter has to stay the same. And so if we make the angular momentum of the blades go up, then we would have to make the angular momentum of the whole helicopter go down by the same amount to compensate for it. And so whatever the change in angular momentum of the blades would have to be equal to the negative change of the angular momentum of the helicopter body right here. And so if that were true, then that would mean, just thinking about this, that since we have an increase in angular momentum, so the angular momentum, our delta angular momentum for the helicopter blades, sorry, I'm going to change my color on that. Get rid of that here. I'll use green for the blades and blue for the helicopter body. So the change in momentum here is going to be positive right here, which would mean that for the helicopter body, the change in momentum would have to be negative, and so it's going to go from 0 to being down like this. And so, well, if that angular momentum is down, then once again we're going to apply the right-hand rule. So stick your thumb down, and and then wrap your fingers around it. And what you notice is by sticking your thumb down in this case is that it causes that the rotation is exactly the opposite direction to that of the helicopter blades. And so for our rotation here is that our fingers will go into the board here. And so for the helicopter, it would go into the board here and then rotate all the way around on the back side of the helicopter. It would come out, which would be, so that means on the front part of the helicopter is that it's going this way, and the back part is going this way. And so it would cause the helicopter's body to start rotating in the opposite direction of the blades when the blades sped up. Now obviously this would not be a very good thing if you're in this helicopter, and so that's the reason why helicopters have the back rotor that's on here. That back rotor can, so in the case of the picture that's sort of in the middle here, is that because of the fact that that it wants to rotate and the tail wants to rotate in that direction, is that we would basically change the velocity of this to act a counterforce that would go in the opposite direction and push the helicopter back there to straighten it out. And so changing the speed of the upper rotor blades, the ones that keep the helicopter in the air, have to be countered by applying basically a net torque. That's what these back blades do, is they apply a torque in the opposite direction so that the body doesn't start spinning whenever you change the speed of the rotation of the rotor blades. So that's something that you have to take into account here. So that would be an example, not including the back rotor, back here, is the way that the body rotates whenever we increase the speed of the blades, is an example of conservation of angular momentum. Now, of course, if we decrease the speed of the blades, then the opposite would happen, is that then our delta L for this would be negative for this, and then that would mean our delta L for the other one would be positive, and so then the helicopter would start rotating, the body of the helicopter is rotating in the opposite direction, and so we'd have to counter it with a torque back in the other direction using the tail rotor. So let's look at this where we not just change the magnitude, but we change direction. So same situation here, but this time, so the helicopter's rotor blades still are spinning in a counterclockwise direction, back around like this. But this time, what happens to the body of the helicopter when the blades tilt forward? So originally, we had a since they're spinning, since the blades are spinning counterclockwise from the top, we said that we're going to get an angular momentum that goes up, sort of out towards us from the perspective of the middle helicopter. It goes up from the perspective of what we have in the second helicopter, in the top helicopter right here. But now what we're going to do is we're going to change the rotation, the tilt of the rotor blades. And so I'm going to exaggerate a little bit, but if a helicopter wants to fly forward, what it does is it tilts its blades so that now they're basically sort of in this new plane. And when we do that, that is going to change basically where our angular acceleration points, because originally it was straight up, but now it's going to be perpendicular to that plane, right? It always has to be perpendicular. And so it's going to be this direction right here. So let's just take a look and zoom out on that and take a look at what this would mean. You know, if our original angular momentum was pointing up with this magnitude, and now our new angular momentum is angled over, it has the same magnitude in both cases here. But you know, if you actually break this down, what you can see is that there's been a change because the new angular momentum has both an x and a y component. And if we look at the change in this, then you know we can actually sort of set this up. So let's look at, for the purposes of doing this, let's look at our change in the angular momentum of the rotor in the x direction, and let's look at the change in the angular momentum of the rotor in the y direction. And let's just, for right now, we're not going to look at numbers, let's just look at whether it's positive or negative. So for the rotor in the x direction, the original angular momentum of the rotor in the x direction was 0, because if you look at that green vector that's right here that points straight up, it has no x component, but it ends up with an x component that goes off, you know, this direction like here. And so if we call this the positive direction, going off to the left in this case, then it would mean that we'd have an increase in our angular momentum in the x direction whenever we tilt those blades forward. Now and that's not a plus, that's just a positive right there. Now in the y direction, on the other hand, is that, you know, originally the whole angular momentum was pointing in the y direction, but now only part of it is. And so, you know, if you look at this, that means there's been a change in that, and that change is negative. And so it means that the change in the y direction of the rotor's angular momentum is negative. But what do we know? We know that if there is no net torque, and so we're not considering any net torque that's in here, that means that if we look now at the angular momentum of the helicopter, and so we'll look at the helicopter in the x direction, change in angular momentum of the helicopter in the y direction. Well, the total angular momentum of the x direction has to stay the same because there's no net torque, and so that means that if the rotor's angular momentum went up, had a positive change, then the helicopter's body has to go in the opposite direction, has to cancel it out, so that the total angular momentum stays the same. And the same thing is true on the y direction, is if the rotor's angular momentum change was negative, it means the helicopter's body's angular momentum change has to be positive. So let's see what that means. So looking at this from this side angle right here, looking at the helicopter's body's change in angular momentum, is we said that in the x direction, the angular momentum is going to be negative, and so negative be pointed back here, and so that means we're going to have a new induced angular momentum that's going to go back that direction. That's our Lx. And then it says it's going to be the positive direction for y, and so it's going to see an angular momentum that's going to be in this direction for y. So we have another one that goes back over there. So let's see what this does. Let's look at just x first. And so we want to apply our right-hand rule. And so stick your thumb in the direction of that x component. So that's going to go back. And when that does that, you'll notice that what it does is that means that the top part, if you just curl your fingers around that, you see at the top of the helicopter your fingers come towards you, and at the bottom of the helicopter your fingers go away from you. And so that would mean that the top part of the helicopter comes towards you. And so we're going to draw that right there. And the bottom part of the helicopter goes away from you. It'll be a little bit like this. So if we looked at this from the front, so we're going to go down the front, we haven't looked at that a whole lot. We said the top part of it goes towards you in the top picture, which would be going to the helicopter's left. And so that means that looking at it from the front here, let's make sure I'm getting that right. Yep, it would be going off the helicopter's left, so we'd see a rotation in this direction here. And at the bottom, it's going away from us down there, which means we'd see a rotation down here. So this would basically, this helicopter would have a tendency, whenever the rotor's foot forward, to rotate, to sort of to tilt over and flip towards its side. And so once again, that's not something that you'd want in a helicopter. We'd have to balance that out, probably by using a tail rotor or using some other factor here. But so that's the first thing. So that's the consequence of just looking at the x change of momentum. Let's look at the y change of momentum. So the y change in momentum for the helicopter body is going up. It's in the positive direction. So let's stick our thumb in the upward direction and then curl our fingers around. And when you do that, what you find is that your fingers go into the board, into the screen, basically on the back side of the helicopter. And so they go away at the back side of the helicopter. On the front side of the helicopter, we wrap around from behind the helicopter, and our fingers come forward on the front side of the helicopter. And so that would come up like this. And so that would mean that in terms of doing this here, the back side of the helicopter is going to start rotating in this direction. The front side of the helicopter is going to start rotating in this direction. Our helicopter would basically, from its perspective, let's see, did I do that right? Let's see, would make a left turn. Am I looking at this right here? I thought it was supposed to come out as a right turn in this case. Okay, so let's see. If the change is negative in the helicopter, in the rotors in the y direction, because it went down, so therefore it must be positive in the x direction for the change in this right here, and so that means it's going to be an increase in that direction, and so our fingers go in at that point and out at this point. So yeah, it looks like the helicopter would basically then start showing a leftward turn, and so whenever the rotors butt forward here. And so you can see from this that just a change in the orientation of something that rotates can result in changes in the orientation of other parts of the system if there's no net torque on it. And so that's something as a helicopter pilot you have to deal with pretty often. The same thing happens with rotored airplanes, is that whenever they start lifting their nose, they will see a rotation. The plane will start to turn to the right or to the left once they change that, depending on whether they're tilting the nose up or tilting the nose down. And that has to do with maintaining this conservation of angular momentum. Even if the magnitude stays the same, if the direction changes, that can affect other aspects.